One of the most important head losses that we experience in pipeline is called a friction head loss. Friction head loss is one of the most typical one, is denoted by HF. So HF, or friction head loss, is due to the pipe friction of the sides of the pipe. And the formula we're just going to use in our reference book here, in other reference book, they might just have like a different the coefficients, but in here we're just going to have like a HF is equal to lambda L V squared over 2GD. And just bear in mind, lambda is like a coefficient, or it's like a pipe roughness coefficient. In other reference book, you might see lambda is shown by F, like the lowercase f. So this is like the friction head loss is the most popular head loss that we experience, and it happens because of the friction of the sides of the pipe. So the second type of the head loss, which is also very popular and common, is called like the minor head losses. But minor head loss is much smaller than the friction head loss, especially for the line pipelines. And that's the reason it's called like a minor head loss. And it's because of the due to the change in the geometry and fittings. Once we have a fittings, for example, bendings like the joints, or any sort of like the decrease or increase of the diameter, we experience we experience minor head loss, or and that sort of thing. Or if you have like a valve, for example, we experience like the minor head loss. And how we can calculate that one? First of all, it's just denoted by HL, and it's calculated as a coefficient of the velocity head. What is the coefficient? And that the head loss coefficient, minor head loss coefficient, is denoted by KL. KL times V squared over 2G. And similarly, the friction head loss is also denoted by as a coefficient lambda L over 2G times or V squared over 2G, or lambda L over G times V squared over 2G. So it's this the same. Similarly, is just denoted as like the coefficient of the velocity head. And just bear in mind, in the UK system that we're just going to work, if you're just going to see in other references, lambda is shown by F, for example, lowercase f. In the UK system, lambda is equal to 4F. But in the US references, if you're just going to see other like the reference book, lambda is exactly is the same as F. So just bear in mind. There are like two specific examples here. So before going to do that one, let's just look at like the top like the figure here. And if you have like any 2 points, and we have a piezometer here, we have a drop from the, if you have a piezometer drop between the two like the piezometers is denoted by HF, through the distance of L, and with a pipe with the diameter of the D, and with the velocity of V. So HF is denoted by lambda, which is a pipe roughness coefficient, L, length of the pipe between the 2 points, V is a velocity, average velocity of the flow, squared over 2G. G is a gravity acceleration, and D is a diameter. There are two other examples related to the minor head losses here, but other head losses you can see, you can just need to just look it up from the reference books. The first example here is like the sudden expansion, if sudden or sharp increase in the diameters. If you have the pipeline with the velocity V1 in the smaller diameter, increase in diameter, and we have a V2. So V1 converted to the V2, HL can be calculated the difference of the velocity raised to the power 2 over 2G. And just bear in mind, this formula can also be written as a coefficient of the V squared over 2G. But which V is going to be used? So it depends on the reference, and once you're just going to look up. Specifically, if you have a contraction, as a sudden contraction like this one, if you have a larger diameter, converted the smaller diameter from the V1 or the D1 diameter with the velocity of the V1 is converted the D2 diameter with the velocity of the V2, we can have HL as a half times V2 squared over 2G. So this is and just bear in mind, this is the half times of the velocity head of the second pipe. Just bear in mind. So that is but you all the time, you need to just look at the reference to just calculate which one is what. So just look at here, if you're just going to analyze the both formulas of the head losses. First of all, the friction head losses, and look at all the terms of the or the parameters of the head loss and just connect that one with the HF, we can just get some sort of like a relationship, a direct proportional. You can see here the lambda, the pipe roughness coefficient, has a direct proportion or a direct relationship connection with the HF. So if you have a rougher pipe, we have like a greater number or greater value for the pipe roughness coefficient, and hence we experience a greater head loss. Okay, and also the relationship between L and HF is like a direct relationship. So it means that if you have a longer pipe, we will experience a greater head loss. So it's the same. With the velocity, we have like the in the exponential, or in the order of the power 2, not exponential. So if you have like a higher velocity, we will experience greater head loss, but with the order of the 2. And there is an indirect relationship between the diameter and the head loss. So it means that for the larger diameter, we will have a smaller head loss. Just imagine, bear in mind. And for a smaller diameter of the pipe, we will have like the higher head losses. So this is something that we need to just bear in mind. And if we just gonna look at the relationship between the minor head loss and the other parameters of the minor head loss, we can say specifically the velocity has got the same as like a friction head loss, direct relationship with the like the raised to the power 2. So with the larger velocity or changing the velocity, we will experience a greater minor head loss as well. And specifically for the minor head loss, specifically for the minor head loss, due to the expansion and contraction, normally we have a lookup tables and different references are available, and you need to just look at that one to just calculate the exact value of the minor head losses for expansion and contraction. Look at these two like the tables here, for example, graphs here. The graphs here, for example, here on the left-hand side, bottom left, we have like a contraction. The diameter or the cross-sectional area of the A1 is converted or changed to diameter D2 or the cross-sectional area A2. So we have, depending on the like the ratio of the A2 over A1, you can easily calculate the KL from this kind of like a lookup, like a graph. And KL can be used in this formula, and KL is used as a coefficient of the V2, the second pipe. V2 squared velocity head of the second pipe. V2 squared over 2G. Similarly, if you just look at on the bottom right figures for expansion pipes, A1 or D1, diameter compared to the D2, you can have, depending on the ratio horizontal axis, a ratio of like A1 over A2, we can easily calculate the KL. The KL is calculated here and as a coefficient of the V1 squared over 2G. So this is like the HL is calculated here. And the other things, let's just look at these like the top figures here. We want to see, for example, here you have like a reservoir, and there's like the a pipeline in taking the water or the flow from this kind of like the reservoir. We want to see what's the like the dynamics and what's the like the impact of the minor head loss. For example, look at here. Look at the like the, for example, in the figure A. You can see there's a like a little bit more struggling of the flow convert or flowing through this kind of like the pipelines here. So obviously for figure A, the coefficient is relatively high. For example, you can see here like a KL for the figure A is like a 0.8. Okay, if you're just gonna try to just have like a little bit trim this kind of like the edges. So for example, you can just cut this kind of like the edges and can have like a better fitted here. You can have like a sharp edge, and KL or the minor head loss coefficient is reduced to 0.5. So if you're just gonna have like a little bit, I mean, in shape B, if you're just gonna have like a little bit like the polish the edge here, and you can have like a slightly rounded, so in figure C, you can see KL is minimized or is reduced to like a 0.2. 0.2. Imagine it's like 4 times like smaller than this, so you can reduce a minor head loss 4 times less than the figure A. And in the best case scenario, if you're just gonna have a well-rounded, in here you can see like the bends like really like the mild and insensible, and you can just reduce the minor head loss coefficients to like the 0.04. So imagine compared to like the figure A, it's like a 20 times less. So the 20 times less is, you can see here. So I mean, this is like for entrance for the pipeline from the reservoir. But if you have like for example a flow discharging, for example, from the pipe to the reservoir, like in figure A, and we have the same simulation, figure A, figure B, figure C, and figure C. This is like there's no like cutting or adjustment. This is like an adjustment here at the order. These are slightly rounded, and this is like a well-rounded. Interestingly, for the outlet, you can see all the like a coefficient, minor head loss coefficient, all of them are 1. So the simple conclusions between and left figures and right figures is that if you have like a flow discharging from a pipe into the reservoir, you don't need to spend a lot of like efforts, money, time to just try to just make it like a well-rounded, because the minor head losses are completely the same. It's the coefficient 1. However, if you like getting the water from a reservoir through a pipeline like here, it's really important if you're just gonna make it like the well-rounded compared to like this one, which is not going to be any kind of like adjustment, you will have a 20 times difference in the minor head losses or the energy head losses. So this is really important. The next thing before we're just going to go to some examples is that normally we have like a lookup tables for the minor head losses. This is taken from the reference book. And or for any reference book of the pipeline system, you will see the same like the similar tables. And that those coefficients, depending on the type of the bends, or it could be like a shaft, well, or any kind of like a bend, elbow, or any kind of like a valve you can see here, and you can see like the minor head losses. Some of the values are less than 1, some of them are like close to 1, and for specifically for the gate valve, you can see the fully open. If it's the gate valve is fully open, like the coefficient or the minor head losses is as small as or as little as like a 0.12. For a quarter close, it's like and a 3/4 open, is the coefficient is 1. Half close like a 6, and you can see here 3/4 close, the minor head losses becomes like a 24 times of the velocity head of velocity of the releasing the pipe. So you can see how big is that once you're just going to have like a changing the valve and try to just close that one. So this is the minor head loss.